would be safest. So each one of these, with varying levels of difficulty, hopefully, if I did my job right, it did our expectations. I forgot to mention that this first one, it said in the homework that it was from the global version, that the US version has a different, and it's not just slightly different, it's very different. So my apologies for not mentioning that. I did put an image of this on Moodle. So if I ever have one where it's very different in one or the other versions, I'll make sure that this is on Moodle. Let me just show you where it is since I'm talking about this right now. Oh, I'm looking for these. They're hanging. I've gotten so bad that I actually have to have them hanging off my neck. Otherwise, I won't be able to see close up. Come on, just a sec. Move, over. Okay. So anyway, just so you know, anytime, so here's what I did is on the homework you can see it says 13 global, says from the global, and then 26 has an asterisk, only because with 28 has an asterisk because even though the two problems were similar, they weren't identical on that one. So if it's ever that they're similar but not identical, I'll put a little asterisk or something there. And then down below, so if we go down far enough, it says problems from the global version of the book. And here, yeah, there's 13. And I put 28 there just if you were curious to see. And if you did the US version, you'll notice that this is really similar. It's not identical though. So since it wasn't identical, I put the global version here. If I ever have one where it's like, oh, the US version is better and the global version is terrible, I'll just put it here as well. So I'll let you know about that. So I apologize for not cluing you into that last time. I meant to, and then I forget what happened. I guess I got excited about something and forgot to tell you. Okay, so let's talk about this dude who wants to buy tablets. So if we can conquer this, the other ones are very similar. The idea here is that you want to list out all the things that could happen and then find the average outcome. So the only thing that is sort of unclear to me is this idea of accepting the gift, whatever that means. But I think what it means is that this guy goes up to daughter number one and says, hey, do you want me to buy you a tablet computer? And she might say no, which, I mean, I don't know why she would, but maybe she's like, no, I don't need one, don't want it. So maybe she's a Luddite, I don't know. But so that's all I could figure with that. So, and then it says that these are independent of one another. So what you could do, and this is what I'm going to do, instead of worrying about all four of the possibilities, which there are four possibilities, the possibilities are this, that, let's see, we have Sabrina and Samantha. It could be that they both want a tablet. It could be just Samantha wants a tablet. It could be just Sabrina wants a tablet, or it could be that neither wants a tablet. So those are the four possibilities. But because these are independent of one another, what I could do is I could just do Samantha, deal with her, figure out what the expected cost is to the guy from Sabrina, and then I could do Samantha and figure out the expected cost for her and just add the two together. So I probably should have mentioned that as a technique last time, but it makes sense that since these are independent, you can just take one and then the other and just say, okay, it's going to cost me something over here, and then later on I'm going to have to deal with Sabrina or Samantha, whoever the second one is, and then I'll deal with that cost, and then we'll just total up the total cost to this guy. So let's just deal with Sabrina, the older daughter apparently, and there is a 0.9 chance that Sabrina wants a tablet, so yes. And then of course this guy is probably thinking, no, please say no. So there's a 0.1 chance that Sabrina does not want the tablet. So there are the two options. Now, of course, if it's a no, then the cost is zero. So this is a 0.1 chance that the cost is nothing. So here's the cost. Well, let's do probability first. We'll do the probability, and then we'll put the cost next to it. So there's a 0.1 chance that the cost will be nothing. Now we'll deal with if Samantha says, or is it Sabrina? Sabrina, if Sabrina says, yes, I do want a tablet indeed, then there are two that she could choose from. There's a 0.8 chance that she chooses the first one, which is a $600 model. Well, now I've got the probability, okay, whatever. So there's a 0.72. That's the probability that that branch happens because you're multiplying those together. 600, you know the drill. And then the other one's a $450. So that's only a 0.2, so that's 0.18. And that's a $450 investment. So now, once you've got the probabilities, this is the hard part, I think, of any of these expected value things, is sorting out the probabilities and the costs, or the probabilities and whatever it is we're measuring, multiplying and adding. You know how to do that. So 0.72 times 600. Okay, yeah. I've already proved today in another class that I can't handle basic arithmetic today with my brain, so I'm going to do it on my calculator. So 0.72 times 600 is 432. Oh, yeah, of course, it's 432. Sorry. And then 450 times 0.18 is, wait, 450 times 0.18. Okay, 81. Okay, I got a much bigger number the first time I typed it in. And then, of course, this is just 0. Add them up, and we get 513. 513? Yeah. So that's the cost that's going to be incurred because of Sabrina. You could do something similar for Samantha. Of course, the probabilities are slightly different. For Samantha, it says 0.7 chance. I guess she's younger. She doesn't care as much about a tablet. So maybe she's thinking that she'll score a better gift if she refuses the tablet. And then the probabilities are 50-50 here. But, so actually, we could do this in our heads, couldn't we? 0.7 times 0.5 would be 0.35, 0.35. Yeah, you could do it on your calculators. So then add it all up and you'll get the total. But like I said, another way of looking at this is that there are 4 options, not 2. And those 4 options are that they both want a tablet, that just Samantha wants it, just Sabrina wants it, or neither. So either way, you should get the same total once you total it up. So. All right, so anything else about number 13, global? This is the global version. And I just liked it. Well, I liked a couple things. I liked it that this guy's given his daughters gifts. I have 3 daughters, and I don't know, it just seemed like fun. Expected value. Okay, so that's that. Here's these two, 20 and 21. So we can do this. So this is the bet on roulette. This is common for people to say, you know what? I know roulette is, here, just a sec. I railed against the gambling already, didn't I? But here's roulette, is just a typical bet. So just typical bet on roulette is you bet $1 on, say, red. So bet $1 on red. So let's see, outcome. And of course, if it comes up red, you get your dollar back along with another $1. Probability is 18 out of 38. You might wonder, why is it 18 out of 38? Google roulette wheel. Will they let you on campus here? I'm curious. Let's see. Well, I'm using DuckDuckGo, so maybe it will, because you know, it's a much more secure browser. Let's see, roulette wheel. Let's see. I used to have one in my office, a little tiny one, and not a big one. It wasn't a real one. It was fake, little tiny guy. Yeah, look at that. You can see images. So here, images of a roulette wheel. Yeah, so the deal is, there's 2 different versions. We'll use American because we are, you know, United States. But anyway, so on a roulette wheel, there are 38 little slots. There are 18 red, numbered, whatever, you can see the numbers, and 18 black, and then 2 that are green. And apparently the Europeans are more generous than the Americans because they only have 1 green, which means that there's less money that goes to the casinos as a result of that. Because the green one is the one that gives the casinos their advantage. So that's why it's 18 out of 38 for red. And then the losing $1 is 20 out of 38. And so the expected value for this game is 18 out of 38 minus 20 out of 38, which is 2 out of 38 negative, which is about a nickel. 0.057, I think it is. I forget exactly, but you could do the math on your calculator and you'll find it's just a little bit more than a nickel. So every time you bet $1 on roulette, and this is consistent, no matter which bet you do, it's interesting. You can bet evens odds. You can bet on a single number. Single number, and that single number bet, they have the odds, the payout, set up so that there's a nickel. Every time someone bets on roulette, every dollar, a nickel of it goes to the bank, if you will, or the house. So this is a very common thing for people to think that they can game the system, if you will. And so they say, here's a good strategy. You always win if you do this. Bet $1 on red, and if red appears, walk away. You walk away with your winnings, so you've won. But if you lose, then you're going to bet 2 more $1 bets on the next 2 spins of the roulette wheel, and then you quit. And I don't know, does it say this is a gambling book? Yeah, gambling book. This is a bad gambling book, because this is not a winning strategy. So the question is, like, what's the what's the expected value? That's what we really care about, is down here, is the expected value. And to answer part A, we're going to have to actually do some math. So maybe I could set this one up. We won't do it fully, but I can tell you right now that the expected value is negative. So you cannot beat the house in roulette, no matter how you try to game the system. Let me get rid of this, and then we'll do this. Let's see, just a sec. Cut that out. Okay, so yeah, let's just set this up real quick. So here are the options. You get red on the first one, or black on the first one. And if you get red on the first one, you're done. You're not going to do anything else. So if you got black on the first, you're going to bet 2 more times. And it could be red or black. I shouldn't say black, because it might be green. Let's say red complement. Red complement. Red complement. So you lose, in other words. You win or you lose. And you bet 1 more time, red complement. And this is red or red complement. And we know that each of these are going to be 1838s, 2038s. So this is an easy tree to fill out. And these are independent. And so you can just multiply through 2038s to get all of this is 2038s down here. And this is 2038s down here. And then this is 1838s. Okay, so you can multiply for each of those branches, and furthermore, you could figure out sort of how much you've won or lost. So for this branch, of course, you win $1. For this branch, you win $1. For this branch, you lose $1. So you could go through and do the same thing. Here, you lose $1. And then this is the reason why this is a bad idea, is you lose $3. Anyway, you can work out the probabilities of each of those happening by multiplying through, and then once you get done multiplying and getting the probabilities for each branch, so we have outcome, probability, you do your magic of computing the expected value, and that will do it. By the way, the probability that you gain money is going to be this branch plus this branch, and it's going to be less than 50%. I tell you right now, because you can see that, let's see, whoa, wait, is it, hold on, is it less than 50%? How could this be? Maybe that's why this is so tricky, is because it feels right, because you have a greater than 50% chance of coming away a winner. Is that right? Just a minute. So you've got 0.437, hold on a sec, 473, sorry, 473.68. I think that's why this is so tricky. 20 divided by 36 times 18 divided by 36 times, 38, darn it. Yeah, you're right. 20 divided by 38. Can't trust me with a calculator, even the one here. Times 18 times 18, 38. Ooh, 11%. Wow. Ah, I see. So there's 0.118. I may have to actually do this whole thing, but so that's 0.118 plus 0.473. Wow, zero point 0.5, excellent. That's really funny. 0.473, 0.118. Yeah, so the probability of coming away a winner using this strategy is 0.591. Fascinating. That's why it seems so likely that this is like why people are fooled. Okay, because there's a better than 50% chance that you walk away a winner. But the problem is this. This is the problem. So, you're going to lose $3 enough of the time. And I'll bet that if you work out the expected value, it's going to be a nickel for every dollar you've bet. Of course, you're betting different amounts here, but yeah. Oh, it's just so fascinating to me that people try to game the system, but they're going to be losers. You know how you become a loser? You go gamble. Guaranteed. Okay, enough of that. Yeah, and even if you win the lottery, I've heard that if you win the lottery, it destroys your life. So, I don't know. That may be just apocryphal, but it's good enough for me to feel good about my choice not to play the lottery. Well, that plus the fact that I'm opposed to the lottery. Okay, what do we got here? Anything else? So you've got, and this is like a perspective thing. So that you just have to be careful about what is X and what is Y. And then these last couple, we have number chosen at random. Let's see, which question? I see, yeah. Okay, so how many guesses on average are you going to have to make in order to get, to find the thing, to find the number? And of course, letter B is going to be much more efficient. And you might wonder, how do you do that? Well, you say, is the number greater than 5? That eliminates half of it right there. So, and that it requires fewer. I think on average, three questions. Is it? I don't know. And what's that?
How would you do A?
So with the A, so the ith question is it I? So there's a 1/10. So this is a randomly chosen number. So so there's a 1/10 chance that you get it on the first guess. And then there's, so here we go. So here's how I do it. So guess, and then probability. So there's a, to get it on the first guess, the number has to be the number 1. So it's a 1 in 10 chance. To get it on the second guess, the number has to be 2. So there's a 1 in 10 chance that happens. And the reason why it has to be 2 is because if you're not going to guess a second time if you got it on the first guess. So yeah, so just if you think of it that way, then there's a 1 in 10 chance of each of these. And so then you just multiply them together, 1 times 1/10, 2 times 1/10, all the way up to 10 times 1/10. Add them up, and I think you'll get 55 out of 10 when you add up all of those. Is that what is there a back of the book on this one, or? No? Oh, no, 55 divided by 10, 5.5. Isn't that the right answer? 5.5 guesses?
Where are you getting 55?
Okay. 4 times.
Oh, multiplying. Okay, I was sorry. I was like,
Okay.
I get it now.
Okay. It's like you're incredulous, which means I'm not communicating. So thank you. I got to do a better job.
You're just doing the X times the P.
Yeah. So then,
I wasn't ready for that.
Yeah. Sorry. XP. There it is. There, just in case. This is for Jaron because he's going to be watching this later. 4/10, etc. And then you add those up. There it is. 55. Sorry, I skipped a step. It's typical of me, right? Trying to show off, just bring it back a notch. All right, yeah, so then add those up. So it's about 5.5 guesses on average if you do it that way. And then if you split it in half, You could think of it this way, that, let's see, each time you split, let's see, okay, give me a sec. I think I've got enough branches now. Let me check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, I have too many branches. How did I have so many branches? Oh, I know. I have too many. Let's get rid of those. Here we go. Okay, so here's how I would do this. And sorry, it's such a mess here, but I would first of all say, is the number greater than 5? So either it is greater than 5, which puts me on this branch, or it's not greater than 5. So this is the 6, 7, 8, 9, 10, and this is the 1 through 5. And then if you say no, it's not greater than 5, I would say, is the number greater than 3? And if you say yes, then I'm down here on the 4 or 5, and then I just have one more guess, and I'll get it. And then if it's not greater than 3, then I have to distinguish between 3 different numbers. So anyway, you can sort of sort things out in a way that you could figure out what your guesses need to be to do this. Yeah, wow. And then the teacher, 5 students, 11, 10. Expect a number of females. Did you get that one? That one's pretty straight. That one's actually the most straightforward of the bunch, isn't it? Because it's either 0, 1, 2, 3, 4, or 5. It's just kind of a pain. It takes a bit of time to write out all those probabilities. Wow. Well, I've got something I've written out most of the probabilities for you for this game of Chuck-a-Luck. You've played Chuck-a-Luck? No, it's a gambling game that you see at fairs often. You may have seen it. You may just not have known it was called Chuck-a-Luck. But anyway, here we go. Let's get this one to go. Give it a try, and then we'll trade here. Here, you can have enough for your friends behind you. There's maybe enough for your friends back there. I'm going to bring one back special. Just in case I mess it up. I'll put Chuck-a-Luck up on the screen here. Got it. Where is it? There it is. There. Do I have dice? Yes, I have dice. So I have dice, if it'll help you. I've got dice up here if you want to borrow some. If it'll help you out, it's easy here. And you can take 3 and imagine playing Chuck-a-Luck, and you bet on, like, if you bet on 5, roll, oh, I got no 5s, so I'm a loser. I'll do it again. I got a 5, I win. I win $1. So anyway, that's the idea there. And I've got the probabilities. I thought that getting 1 die to match your number is kind of hard, and getting 2, it's hard to compute. So I put those down, but 0, that's easy. And I think you can do all 3, the probability of all 3 of them matching your number. Oh, they're all 5s. No, they weren't. Just kidding. So, and I'll Google this or DuckDuckGo it to see if there's an image of Chuck-a-Luck. Pull this back. Ooh. Oh, I can take the homework, I guess. Snap it up. There's homework up there. First, very nice. You're all done. Good job. Let's see if I got it right. Pretty good. This one, didn't want me to do it? That's okay. This one wasn't too bad, was it? Ooh, it's all coming together. This here. You're all set? Done? Good? Good enough? Oh, you did it in red. Excellent. Make it more exciting. I'll use green for yours. Nice. Okay, I think I got all of them. Do I have all the quizzes? Leave that there. Let me staple these together so they can be together in friendship and joy. Okay, so let's see what I did. First things first, we need to know the probabilities of 0 matching your number. So like you're picking a number. Oh, I did look up. Here, a sec. I looked up Chuckaluck. Where is it? I did DuckDuckGo search, and here's what I got. So I was very excited, although I was surprised. So there's all these images. So apparently this is a gambling game, like that you could go to like a casino and play. Of course, I've never been to a casino. So closest thing I came to a casino was I was in the Las Vegas airport, which is like a casino. But this is what I remember from being a kid going to like fairs. They'd have this thing that looks like a cage thing, and they turn it over and the dice roll, and they have like a pad like this. So that's kind of what I remember, or this as a kid. But yeah, it's a thing. So apparently the casinos though do this. Okay, so let us go on and see how this works. So the first things first, we need to know these probabilities. Then once you have the probabilities, it's pretty straightforward. Although I realized that there is one nuance that I kind of left off here, but we'll deal with it. Some of you might have noticed, maybe you didn't. Doesn't matter. Okay, the probability of none of the dice matching your number. So in my fictitious example where I bet on the number 5, I want none of these dice to be a 5. So there's 216, that's 6 to the third, 216 ways of rolling. Oh, 664. But for this one not to be a 5, there are 5 options for that, 5 for this, and 5 for that. So it's 5, 5, 5, or 125 out of 216. And then for this, for these 3 dice to land on my number, all 3 of them, I have to have the 5, one choice. I have to have the 5 here, one choice, and there's only one choice for this one. Okay, so that's that, 1 out of 216. By the way, if you're curious where these numbers came from, how many ways can you have one of the dice be your number? The way you would do that is you pick which of the 3 dice you want to be your number, 3 choices, and then the other 2 can be any of 5. So this could be 5 choices there, 5 choices there. So that's why that's 75. And then this one, to be honest, the way I figured it out is I subtracted from the rest of them from 216, because it has to add up to 216 over 216. Okay, anyway, multiply through. 0 times this is 0. 1 times this is 75 2/16. 2 times this is 30 2/16. 3 times this is 3 over 216. Add them up, and you get 108, I think. Is it 108 out of 216 as the total? So the thing that I did not mention is that is your average winnings if you're betting $1. So I guess that what you could say is that if you bet $1, you expect to get back about 50 cents, which means you're losing 50 cents for every dollar that you bet. So yeah, it kind of got lost in the nuance. No one, I don't think anyone did this in the way that it should have been written. Ooh, wait a minute. Huh? You know what? I think I might have been wrong about this. Well, let's leave it the way it is, because I think I saw a lot of 1/2s there. But I think what I should have done is I should have been, if none of the dice match your number, you lose $1. I think that's the way it should be calculated. And then if one die matches your dollar, you keep your dollar and you get an extra $1, so that's a gain of $1. So this is like your wallet. What happens to your wallet? You lose $1 because you have to pay to play. And then this is, so I think we all, if anyone did this, then you're the winner. Anyway, so this should be -125. Let me do this right. So this is -125 out of 216. So in truth, it should be -17 out of 216. Wow, that's actually quite small. So on average, you're only losing. Is this less than roulette? No, that's more than roulette. But still, it's a pretty small amount that you lose. So it's pretty easy to overlook that you're losing money over time when you play these sorts of gambling games. Okay, so expected value. I was going to use this for my example for variance, but now I don't like it anymore. Let's use something simpler. Let's just do a regular die. We'll do a die. Yeah, just a regular 6-sided die. Okay, so instead of pulling up the PowerPoint, let's just do this and mention that the expected value of a function of a random variable is computed by doing the same thing that you did to compute the expected value. You add up the function times the probabilities. So you might wonder, how in the world, what does this mean? Well, here's one way to interpret this. Let's say we have x and p of x. So 1, 2, 3, 4, 5, 6. Sorry, there's 6 dice. 1/6, 1/6, 1/6, 1/6, and 1/6. Okay, so there's a die. There's my die. But let's say that instead of just rolling the die and recording the number, let's say that I roll the die, I got a 6. Then I go over to the board, and I pull out my protractor, and I carefully draw a circle that is 6 inches in radius. Okay, that is bigger than 6 inches in radius, I realize, but whatever. So I draw my circle that's the same as whatever the die is, and then I compute the area of the circle. Pi times 6 squared, 36 pi. So if I did this, one question you might have is, the area of the circle that I get is a random variable of sorts. It's related to this random variable, but it's random, and I could ask myself, what is the expected value for the area of the circle? And the expected value for the area of that circle is going to be the expected value of pi times x squared, where x is this number here. And then to do that, I just add up each of these, so it's going to be pi times 1 squared times 1/6, plus pi times 2 squared times 1/6, and so on and so forth. So you could do this yourselves. I'm not going to compute this fully because I don't really care what that is, but I need to mention that because we're going to be computing the variance. And to get the variance, we need to understand that idea, that you can take a function of a random variable. Okay, so now the variance. I'm going to do this 2 ways, the hard way and the easy way. So I got to show you the hard way first because it's just I'm contractually required to. So the variance of a random variable is literally the expected value of the outcome times the mean. Let's actually use expected value here. Expected value squared. Now, if you think back to, I offended you? No, I'm just kidding. It's videoing, so I hope you crushed the competition. She's going to soccer it up out there. So go down to see soccer, CH4 Stadium. It's going to be exciting. Maybe. I don't know. Is it? It is? No? I don't know. I thought you had a comment. All right, so I don't know if you remember from statistics class. Do you know what the variance is from statistics? It looks sort of like this. Let me show you. I actually did this just yesterday, or I'm sorry, Wednesday in my stats class that meets in the morning. Here is the formula for variance. Variance looks like this. So maybe you recognize that, maybe not. But here, I'll just explain what you do. You take the average for the whole, like, average height. Average height, 69 inches for guys, 64 for women. You take your height and subtract off the average height. So for me, it would be 73 minus 69. Square that, and then we take all of our numbers and average them together. That's what variance is. Variance is the average squared difference from the mean. So that's all it is. And so notice what I've done here is I'm doing the average. That's what this means, average. The average of the difference from the average. Okay, let's do this for a regular die. Now, like I said, this is the hard way. So my apologies, but we have to do it this way once. And then we'll do it the easy way. Okay, so this to show you that they're the same. Algebraically, they're the same. I don't know if we'll have time to prove that they're the same. Probably you're thinking to yourself, please no. We don't need to prove. We just will trust you. Okay, so we have x. We have the probability. And then on my chart, I'm going to make another couple of columns. So we have x minus the average value. Sorry, it's going to be a little bit messy here. And then I'll do x minus the average value squared. Like I said, this is the hard way. Okay, and then finally, I will do x minus the average value squared times the probability. Okay, so 1, 2, 3, 4, 5, 6. Probabilities are 1/6 all the way down the board here. Turns out that the expected value for a fair six-sided die is 3.5. If you don't believe me, go ahead and add it up. You have 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6, and so on until you get to 6 times 1/6. The total is 21/6, which is 3.5. So you'll just have to trust me. Now I'm going to do x minus, let me clean that up. That looks ugly. Clean it up again. Still looks ugly. That's better. Okay, x minus the average is going to be negative 2.5, negative 1.5, negative 0.5. This is 0.5, 1.5, and 2.5. So this column is just each of these numbers minus that. Okay, next we're going to square that number. And the reason we're going to do that is because if we were to just average these together, you can see right off the bat that this column, if you were to average those together, you get 0 every single time. That's one of the properties of the mean. The mean is the middle, and if you average together the difference from the mean, you always get 0, always, no matter what data set you, doesn't matter if it's skewed, symmetric, uniform, I don't care what it looks like. Okay, so there's that. Now let's square this. So 6.25, 2.25, 0.25, 0.25. So the benefit here is that when you square these, you end up making everything positive. Now we can go through multiplying by so basically we're going to be adding these up and dividing by 6, but because we're doing this, because we're probabilists, we're going to multiply and then add. So it's the same thing, but it's just not going to be quite as clean. Okay, here, let's do it this way. 6.25 over 6, 2.25, because it'll come out some nasty decimal if I just 0.25 over 6, 2.25 over 6, 6.25 over 6. This wasn't too bad. Now that I think of it, this really wasn't that bad. So the variance is equal to this number right here, whatever I get when I add those up. Let me see. So that's 6, 12, 12, 17.5. Is that what I got? 17.5 over 6, I think, which is the same as 35 twelfths. That wasn't too bad. Is that right? Did I get it? I did get it? Oh, amazing. All right. I got to get it done before we have to leave. So, okay, so that was the hard way. But the hard way wasn't that hard, was it? Wasn't that hard. But you can imagine that especially this business of subtracting off the mean, it can get a little clunky and a little difficult. So let me show you the easy way. So that's the hard way. Let's see. Let me write this down here. So, oh, there it is. No, that's just the formula. I'll just write it here. So this is the hard way, is that you do the expected value of x minus e of x squared. And that's the variance. Okay, so it turns out that there's an easy way. Easy way. And these are, oh, I don't have my book with me. These two methods are algebraically identical. That is to say, if you were to write out all of this, and especially if you were to take that and expand it and then simplify, move things around, collect like terms, take this x minus e to the x, e of x squared. If you do all of that, it turns out that you get exactly this, super easy. So the variance of x is the expected value of x squared minus the expected value of x squared. And that's it. Now, at first glance, this may not look like it's saving you much, but let me just do this really quick using this. So, what's that?
Oh, I just did the wrong homework, so I already knew that that's what it
Oh,
was.
you already knew this? Oh, amazing. That's brilliant. So, yeah, you're all set then. Yeah, you don't need any of this. But we're going to practice it nonetheless. So we're all done with, at least, yeah, you're all done. But let's just, humor me, and let's do it once with this die thing. So notice the amount of work we had to do. This is the die. Let's do the die again down here, but we're going to do it using the easy way. So let's do this. Let me get rid of this thing really quick here. Delete. Come on. Why can't I see the... Sorry, it's really pitiful. Can't see what's right in front of my face. Okay, so basically I'm going to take this same stuff. Here we go. Give me a sec. I'm too lazy to write it again, so I'm just going to copy and paste. There it is. So we're going to start in the same place. And then I'm going to do this. We're going to do x times p, which we have to do anyway when we do the expected value. So whatever, 1 6, 2 6, 3 6, 4 6, 5 6, 6 6, and that gives you the expected value of 3.5. So that we had to do anyway. That's the expected value, the average value. Okay, now what we're going to do is we're going to do x squared. So there's no subtracting or anything, just do x squared, and then do x squared times p. So x squared is 1, 4, 9, 16, 25, 36. So now I do x squared times p, so 1 6th, 4 6th, 9 6th, 16 6th, 25 6th, 36 6th. So of course, if your distribution wasn't uniform like this, all the same probabilities, then the probabilities wouldn't look as uniform as these do. So, but anyway, add this stuff up, and this is the expected value of x squared, which apparently Sarah's already done. So you don't have any homework this weekend. So let's see, this is 40, let me add this up, 40, 50, 75, 85, 91? I think it's 91 sixths. That's what I'm getting. Does that look all right? 91 sixths? All right, now we'll just do the final bit is the variance is going to be this number, 91 sixths, minus this number, which apparently is 7/2? 7, is that? Wait a minute, 7/2 is 3.5. Yeah. Squared. So that's it. So let's see, this is 91/6 minus 49/4. Okay, now we would probably pull out our calculators at this point, wouldn't we? But you know me, I can't use a calculator if I can help it, so let's do this. 150, so that's 147/12. And subtract this, and I get 35/12. Did I do that right? 35/12, let me double check. Oh, look, it's the same. Okay, so exciting. So it's the same, exact same thing, very nice. So 35/12 for both of those. So let me just clean this up just a bit, because it bugs me. Okay, so that almost is all that we need for the homework. There's one more little thing that I want to make sure I mention. So let me just pull back here real quick. That way we don't, because I don't want you to, I don't want you to get frustrated on your homework. So let me just take a peek here. I've got this right here. Where did I put it? Oh, I put it back here. Okay, so the homework, we've got just 3 problems. You did the 3 problems on the homework, Sarah? Amazing.
Not well, but yeah.
Oh, yeah, I cleaned them up for Monday. Okay, so let's take a peek here. Let's see, because I think there's something weird on one of them. I want to get you started on it. So we have 35, which is 2 cards drawn at random. Expected value is pretty easy. So you're going to set up your probability distribution, and then the expected value, that should be easy enough. And then to do the variance, which you know is related to standard deviation. So if you do the variance, you just do the expected value of x squared. So you figure out, okay, you win $2, you square that, you get $4. You win $1, that would be square that, it turns into 1. And then you square negative 50 cents, and you get positive 25 cents. But anyway, that's easy enough to do the variance there. But the one that I think, let's see, let me get you started on this one. Is it 39 is the weird one? 39. Ah, yes. Yeah, let's take a look at 39 real quick. And then let me just see. What's the last one? 43? See, look at this. I was super short today. 43. Yeah, this isn't bad. Expected number and variance. Okay, yeah, let's take a look at 39. I'll get you started on this one so that you know what to do. So it looks like you're given so little information, doesn't it? You're given that the expected value of some random variable is 3, the variance is 1, and you're supposed to come up with all kinds of other information. So let me get you going with this one. Hold on a sec, so that we don't have to spend as much time on Monday. Copy, because Monday we're going to be starting with Bernoulli random variables, and those are super fun. So here, let me put this over here. So we don't want to waste any time on Monday. Okay. So here's your information. So let's start with, wow, these are complicated. Let's start with this. You have the expected value of x is 3, and the variance of x is 1. Your job, so I'm not going to do this completely for you, but I will get you started on it. Your job is to come up with the expected value of x squared using this information here. So see if you can work that out. That'll be the start. And then we'll talk about how to conquer those 2 problems up there. So take a minute, see if you can do e of x squared. Oh, I should have randomized you. Let me do attendance while I'm, or did I do it? Oh, I did do attendance. That's good. Yeah, I can randomize. Yeah, let's do this. All right, Reagan, do you remember what the variance formula is? Just the formula.
The easy one is the e of x squared minus the e of x.
That's it. Very nice. You squared this one, right?
Yeah.
Okay. Nice, good. Okay, so that's the variance formula. Hey, hi there, they can come in, yeah. Just a sec.
Are they bringing us cookies?
No, no, nothing to be sorry about. No, yeah.
We don't want to be, sorry, we didn't want to be too loud.
Oh, no, you're doing
Yes,
great.
we didn't know that there was,
Yeah.
we still didn't know that there was.
So
a
wait,
house next
Jacob?
door.
Jacob,
Yes.
Alyssa?
No.
Alyssa,
My
Alyssa,
name's
Gabby,
Gabby.
Yeah, and Cam isn't here.
Camden.
Cam is not here.
Oh,
He's,
you're not-
yes, that's sick.
He's sick.
Carter's helping
Oh,
us.
Carter's helping us, okay, very nice. Oh, hey, they brought us cookies, isn't that kind of them?
Fresh. They're probably still warm. Yeah, there's one cookie, one Rice Krispie treat for everyone. So you want to start over there where Gabby's giving us. Yeah, sorry, we just totally hijacked.
Oh, no, no, no. I was actually stalling.
You were. We were just admiring your dedication. We were watching you for a little while. I was like, he's so into that math. He's smiling.
Thank you.
It's beautiful.
Well, I think it's some chocolate feeling better.
Chocolate fountain, Jacob. That sounds fabulous.
The strawberries and sticks.
So I told them all at the beginning that we were hoping that all of that noise would result in something good.
Okay. And it did. So we apologize if we are a little noisy on a Friday afternoon.
Well, it should be something new.
Good things are happening in there.
This ameliorates any bad feelings, I'm sure, so it's all good.
They're still a little warm, I think, so they're a little sticky there. Sorry.
Do you want any napkins?
Oh, you know I do. Thank you. Thank you so much.
You're welcome.
So do you make cookies every week?
It just depends.
So it depends on what you do? Okay.
Last week we talked about healthy nutrition, and then the week
And then
before and the
make
week after we made cookies. So I mean, it's
That's
all
your
about
own
balance,
doing.
right?
Yeah, that's
Your
what I was
own
gonna
doing.
It was my
say.
own doing, right?
It's a balance. Very.
And a dozen,
Delicate balance.
and a dozen is 12.
Are our numbers working out, Alyssa? Are we okay? Okay, good. Phew.
Oh, yeah.
Yeah, my sister used to.
So Jacob's not here today.
Chemistry.
Oh, Jacob is here. Camden's
is-
not here.
yes, yes.
Jacob, it's good to meet you. Alyssa, I can only eat this one because I have a chocolate problem. Which is tragic, you know, when you get old, certain things
Right,
don't agree with
okay.
you, but thank you so much.
Well, happy Friday, everyone.
Yes.
Friday.
All right, we'll finish this and then we'll party it out of here. So I just wanted to point out that you take this, I don't know who I was going to ask. I guess Reagan's the only one I got to ask. But then you take this stuff and you're looking for this number. Yeah, you can plug in the 1 and the 3. And then as far as this goes, what you can do is you can rewrite that as e of 4x quantity squared plus, minus 8x plus 1, which is the same as e of 4x quantity squared minus e of 8x plus e of 1. And so that's 4 squared is 16 e of x squared minus 8e of x plus e of 1. Okay, so the reason you can do this is because these are summations. You're adding things together. And so essentially you're going to take the thing you're adding together and separate it into 3 summations. That's all that is. But so the e of 1, what's the expected value of 1? If you get a 1, if there was a die printed with only 1s, you'd expect to get a 1, right? So that's what that is. This e of x is there. E of x squared is, you're going to get that right here. And then you can put it all together. And then the variance, you can do something similar, little trick with the variance. Just remember that the variance of this will be the expected value of that squared. So it would be like expected value of 5 minus 2x squared minus the expected value of 5 minus 2x quantity squared. So you'll have to do a little bit more arithmetic. But yeah, this one's weird. I wanted to make sure we hit that. I was also stalling just slightly because Dr. Tenney, had suggested that as a penance for being loud, that she would bring some cookies over. So anyway, thanks for sticking around, and hopefully you won't die on the cookies aren't choking on them, are they? So a little bit of, you forgot how to drink water. Okay, very good. So apparently they were just standing there waiting. They could have barged in. I should have told her.
Trying
All
to
right.
get collected.
Nice. Excellent. Red pen, I love it. I'll stick it in the stack here with the rest.
Hey Zane, do you want extra Rice
Yes,
Krispie
does
treat?
anyone want an extra one?
Oh, I got one here. I'm good.
Well, here we go.
Mm. Are you allergic to Rice Krispie treats?
They have gluten in them, and I can't have lactose anymore as well.
Oh, you're like officially.
So I'm officially celiac.
Oh,
And then,
you are.
in order to heal my gut, they said I have to go off lactose as
Oh,
well.
no.
Okay.
Oh, I'm so sorry.
It's okay. It's
Pamela's gluten-free flours are so good.
Yes.
And then I have a source. I buy oats from this place in Montana in 25-pound sacks.
Oh
And then-
yeah, yeah.
Because their oat fields are separated from wheat by miles and miles.
Yeah.
It's just, yeah, it's a pain, but you'll figure it out, I'm sure.
Yep.
So, it's good to know what the problem is.
Yes, definitely.
Mm. And isn't it offensive to you that Kellogg's Rice Krispies have gluten in them?
Yeah, it's like the dumbest thing. It has
But
some
why?
like malt
Yeah,
flavor or
barley
something added.
malt,
Yeah.
unnecessary.
Yeah, exactly.
Incredible.
Completely unnecessary.
Mm-hmm.
Have a good weekend.
Yes, take care. See you on Monday.